Okay, today we're doing kind of a double day. The first few minutes is about the old stuff, and actually it was just going to be a review today, and it was so easy. I hit it pretty hard yesterday, so I think you're going to agree that you'll totally understand the first few things we talk about, and we will shut that file and move on to the next one. The plan right now is that we are going to be testing on Tuesday. It was going to be Wednesday, but Wednesday is going to get destroyed by the PSAT. And then I thought I'd push it to Monday, but then that means I have to add in an extra review day. And if I do all of that, we will literally be taking the test next Tuesday instead of this Tuesday. That's like putting us back a week, which would mean I'd have to go really fast in the following unit, which is more difficult. This is actually one of the easier tests that we have. Today's got a couple challenging things because I'm adding in tomorrow's lesson. So anyway, bottom line, we're testing on Tuesday, and this won't be too tough of a day today. All right. Do you remember that if you're going to take a point like this, the x goes in to that spot, and it doesn't go in here. You don't put a 2 there, but you say 2 equals x plus 3, and then you'd solve it, and then what would the answer be? -1, comma, and then if this point were going to be transformed, the y part of it, the y part goes in, the -3 goes in where the f of x was. The whole thing becomes -3, and so this becomes -3, so the answer is -3, -1, -3. All right, I think you remember this. We'll see. Here's g of x, and it's made up of the original f of x, except you double it, and on the inside we're going to have 3x minus 1, and then plus 7. If this point, 5, 1, was on f of x, then what's on g of x? What is the point that this would turn into on the new function? I'm going to pause and see if you have got those straight. This is the same thing as yesterday. Nothing new here. Pause for a moment while you try that. You should have said that this 5 here is set equal to this. So 5 equals 3x minus 1, add 1 to both sides, 6 equals 3x, x equals 2. Raise your hand if you had x equal 2. Okay, good. The other part was the 1. The 1 is the y. Where does y go? This whole thing is y. F of x is this whole thing. So that becomes a 1. That's a 1 in there. And now it's 2 times 1 plus 7 makes 9. So it's 2, 9. Raise your hand if you had that one right. Good. So half your assignment for today was going to be those. Come on, you already got those. So the other thing from this assignment was a review of something I taught you heavily yesterday, the order thing. Y equals -3 times 2x plus 1 squared minus 7. Do you get that has 1, 2, 3, 4, 5 things going on? 5 changes, 5 transformations? And I taught you how to do that in the right order. The only thing I never messed with was the distinction between a -3 being actually 2 things. It's like a -1 for the flip, or the reflection, and times a 3 for the stretch. But if they're both multiplies, does that really change the order at all? No. So does it really matter whether you do this one first or this one first? Nope. Since they're both multiplies, they can go at the same time. You can do one before the other or the other before the one. It does not matter. I will tell you in actual graphing and actual practice, it's easier to stretch something before you flip it. Because if you got the parent function already, it's easy to take that parent function and stretch it before you flip it. Because once it's flipped, everything seems all backwards. And besides, it works better in gymnastics to stretch before you flip. But that's optional. So I want you to make me a list of 1, 2, 3, 4, 5, and I bet you 75% of you will get an order that works. Give it a try. See if you can get the order right. Pause while you do that. You should have said that you go on the inside first, and when you're on the inside, what comes first, multiply or add? Well, normally multiply comes first, so it doesn't go first. You got to do the add first, because this goes the opposite of normal order. You should have said left 1. Raise your hand if you started right. If you started right, then you're pretty much going to end right, because then there's only one other thing to do in there, which is that. And then some people do mess this up because it's not a stretch. It's a horizontal shrink. And you can't say factor 2, you have to say factor 1/2. And yes, you should throw the word factor in there. You're all grown up now. You can't just say stretch 2 or stretch 1/2. You say stretch factor of 1/2. All right. Then the third thing is either these can be reversed, because these are these two, because they're multiplies, and they come before subtracts. On the outside of the function, you do the normal order. So I'm going to say that the stretch before you flip is a good idea. So this is going to be a vertical stretch factor 3. And then a vertical reflect. And notice I don't have to say over what axis because I said vertical. Now it happens to be over the x-axis when you go vertical. That's going vertical and it's going over the x-axis. All right, so last thing, the 5, is down 7. So here's the question. Yes, sir. So you do not have to worry about the squaring because it's not a change to the function. Do you get the original function would have been y equals x squared? All we're talking about is what changes did we make to the function, so you don't have to do the squared, yes. All right, do you get that I might instead give you a list of things to do and make you write that function that I just scribbled out? You know what I'm saying? So skip ahead in the notes to where it says, right here's the other part of the homework. It wants you to write a square root function that's been shifted right and down 3. Right 2 and down 3. Why don't you write me an equation for that? Kind of like the opposite of what we just did. Instead of saying what happened, they're saying this happened. What was the equation? And right 2 is this, and down 3 is that. There we go. There's another way you could have done it, which is to say g of x is my new function, and it's the old function. Notice me throwing an f in front of that. That's another alternate way you could have written it. Gentlemen, stay with me, please. Apparently page 13. All right. Okay, one more. Would you do 55? It's got a little bit of a twist. Notice it has to be in this order. Down 3, isn't that like this? Down 3, and then right 2. All right, now, some people are going to get confused by this because they're going to be like, Mr. Server, you always told us to start on the inside, so shouldn't this one go right 2 first and then down 3? Do you remember me saying that I suggest you start on the inside, but it's actually also legal to start on the outside, do all of that first, and then go to the inside? This is my moment that I'm reminding you of that. You don't have to start on the inside. It's my advice because I think people screw up less when they do that. But if you want to start on the outside and finish all the outside things first and then go inside, it's legal. That order works too. And I know it's more complicated to have to throw that in there, but it is true. So I need to tell you the truth. Even though starting on the inside is my favorite way and the way I think you should probably do it, you can use start on the outside. Here's what you can't do. Well, then anything goes. Like I can do some of the outside and then some of the inside and then go back to the outside. That doesn't work. And the other thing that's always got to be true, whatever you do on the inside has to be the opposite of what you'd expect. So again, if there had been 2 things happening in here, you would have to do this one first because that's counterintuitive. Everything on the inside is always kind of opposite of what you think. That seems like it should go to the left too because the numbers are getting smaller because you're subtracting from it. But it actually goes right too. So again, things on the inside are always backwards. But you can start on the outside first. So this was a right answer for 55. Okay. That's all you'd have for today. That'd be done. And that's just so easy. So that's why I decided, okay, we're either going to have these super easy slow days and then I have to like run really fast next chapter. Or I'm just going to keep teaching you this hour because that was 9 minutes and 59 seconds, and we can go further than that. So find the other file for today, which was started with this. It says an unusual value. All right, so this is about reciprocals. Did you get that reciprocals are 1 over something? So if I have 8, what's the reciprocal of 8? 1 over 8. You just put 1 over it. It can get more complicated, of course, if you start with 2/3, because then when you put 1 over 2/3, you really have 3/2. Because 1 over something means I'm going to change instead of divide by 2/3 to times by 3/2. And so see why it's 3/2? All right. So a reciprocal of a fraction is 1 over that fraction. And yeah, that flips the fraction. A reciprocal of A would be what? 1 over A. That's the reciprocal of A. All right. Now, this thing is a 1 plus 1 over, and it's this giant, never-ending fraction. Could you shut the door for us, please? Thank you very much. This giant, never-ending fraction, when you actually add it all up, gets closer and closer and closer and closer to this perfect number. The perfect number is the golden ratio. Have you heard of the golden ratio, 1.618? That's this special ratio that I'm going to spend a few minutes talking about here and show you in class. It's a giant fraction within a fraction within a fraction within a fraction. And when you add them all up, if you keep adding this up, obviously 1 plus something is going to get bigger than 1. The something, the 618 thing, the 0.618 thing, is just this nested fraction. And it comes from some pretty cool patterns that I think you saw when you're in elementary school. Let's see if you remember it. 1, 1, 2, 3, 5. Do you remember how this works? And then 3 plus 5 makes 8, and 5 plus 8 makes 13. I'm confident you've seen this before. For instance, the teacher might have told you that the number of petals on a flower is usually either the flowers have 1 petal, or they have 2 petals, or 3, like in a clover. Ever heard of a 4-leaf clover? Isn't it kind of weird and actually so unusual that it's considered lucky? It's actually a mutation. Notice 4 is not on the list. You also have almost no 6 or 7-leafed flowers. There's a few weird exceptions, but of the hundreds of thousands of options out there, they're almost all Fibonacci numbers. This is the Fibonacci sequence. If you find a flower that has a ton of leaves on it, you count them up, I would bet you you're going to end up coming up with not 14 or 15 or 16. The next number after the 13 would be 21. It's going to have 21 petals. If you count the spirals on a, not a coconut, what are those called? On a pineapple. Count the spirals, the little number of little blocks that are in the spiral, and the number of actual spirals that there is, they're Fibonacci numbers. It's just amazing how this comes up so often in the real world. You look at snails and their shells, and you can find this ratio in there. So I'm going to show you something in class here, these sticks that I have that I won't be able to show on the video that tell you something about yourself and how your height and your arm span and stuff relates to the golden ratio. So I'm going to pause while I do that. All right, we're done with seeing the proportions there on the sticks, the 1.618. Just a couple last thoughts on that. Have you ever heard of this moron that was famous for painting the Mona Lisa? He was just an artist. No, actually, he was an artist, and he was like a mathematician, and he was pretty much a genius inventor and a philosopher, Leonardo da Vinci. And when he painted, he used the golden ratio all over the place in his paintings. So, for instance, the Mona Lisa's got it on her in like 3 different spots in that painting. They used the golden ratio. It wasn't just by accident. It's on purpose. So it's pretty famous, and I just wanted you to know about it and know that it was all over you personally. Width of your face, height of your face, divide them, it's probably about 1.618. All right, so hope you learned a little something out of that. This is some kind of cool thing, if I had more time, that I could do that shows you mathematically why the golden ratio works, but that's too much for today. So here is our inverse teddy bear. because we're doing an inverse of a function today. And so that's what 1 over a teddy bear would look like. I know that's a little sick and twisted. I get that. But no teddy bears were actually harmed in the creating of this picture. They put him back together, and he's in a little teddy bear farm now, and he's just going through counseling. Anyway, this is the absolute value of a function, and this is a function that's got an absolute value just on the x's. This one's got an absolute value on the y's. I'm going to show you the difference between those three things today, and that's all we're going to have to learn, and then that will be the last we need to know for the test. So let me show you how these work. I'm going to recommend you get a blank Notability, not even a doc, just a blank page, and start by taking a parabola and making it shift down a little bit, because it'll work better if it's not the normal parabola. If I have this parabola, and I call it f of x, it happens to be x squared minus 4. It's been shifted down 4 spots, let's say. What do you think would happen if I absolute valued it? If I absolute value this, it's the same exact thing as absolute valuing that, right? That means the y's, f of x is like y, right? That means the y's can't be negative anymore, because you absolute valued them. It's going to turn anything that was negative positive. Where are the y's negative? Think about it. Down there. That's where y's are negative, right? So those can't be negative anymore. Anything that was a negative number gets changed to a positive number. So when you input 0, you used to get negative 4. Now you're going to get positive 4. When you input 1, you used to get 1 squared is 1 minus 4 is negative 3, but now it's the absolute value of that, so it's not negative 3 anymore, it's positive 3. Get where it's going? All of these things are going to end up being reflected up there. That one dot's bothering me. I'm going to remove it. So when you absolute value a function, it depends where you absolute value it. If you value it absolute value around the whole function, you are taking the y's that were negative and making them turn positive. And they go like this. How about the y's that were positive in the first place, like here? They don't change, because if they were positive in the first place, absolute valuing doesn't change them. So my new graph kind of looks like that funky looking W. All right, I'm going to give you another one like that and see if you caught what I was trying to show you. Sort of like a backwards check mark. My question is, what would the absolute value of that function be? If this is f of x, what would absolute value of f of x be? You're absolute valuing the y's. So the y's that were negative become positive. Do you get that these are the area where y's were negative? So it needs to pop up. Final answer is this black, sort of like a flying W. A W that's been pulled on or something. Raise your hand if you had that one right. Okay, good. That was absolute valuing a function. But what if you absolute value the inside of the function? Let me show you what happens. Back to our normal f of x. What if we absolute value it in here? Then we aren't absolute valuing the y's anymore. We're absolute valuing the x's. So where were there negative x's that now are going to have to become positivized? These are the negative x's, right? Those can't be there anymore because we just absolute valued them. They're gone. The most common wrong answer is people think it reflects this way. It does not. Because then it wouldn't be a function anymore. Think about it. It wouldn't pass the vertical line test. So here's what actually happens. Now, I'm aware from doing this explanation 8 million times that either I'm terrible at explaining it or it's really complicated and only a few of you will get it. So I'm going to try to explain why this function reflects the way it does. If I put in -2, the function is not going to ever even see the -2. Because when I drop in the -2 here, what'll the function think I put in? A positive 2. So it's going to go over to where positive 2 is and say, okay, well, there's positive 2. Here's the answer for y for that. It's going to think I put in positive 2. And so it's going to give me the same answer as it would have if it had been a positive 2. What if I put in 0? It doesn't change at all, does it? As the value of 0 is the same exact thing. So it'll give me the same value it had then. What if I give it positive 1? It doesn't even know. Absolute value of 1 is the same thing. It's going to give me the same exact thing. So all of these stay the same. But when I put in like negative 3, it's going to think I put in positive 3. And if I put in positive 3, it would have given me, let's say that's the spot where it touches there. It would have given me 0, so it gives me 0. Do you see what's happening here? This stays the same. And this side becomes a reflection across the y-axis. I know that's tricky to understand why that's happening, but at minimum you need to get, I absolute valued all my x's, so the ones that were negative had to go. That's this part. They have to be out of there because you can't have negative x's anymore. And when you're putting in a negative, the function thinks you're putting in a positive because it can never see that there was even a negative. Once it comes out of those absolute values, it becomes positive, and it thinks you're putting in a positive 2. So it gives you the same value as over here. All right, so let's see if you caught that well enough to get this one. Kind of like a backwards N. I want you to tell me, first, what would happen if I did f of the one we just talked about? The x's all got absolute valued. Then, for extra bonus points, sketch what you think the other one would be like, where you absolute value the y's. I'd like you to try both. I'm going to pause while you give that a shot. So here's what you should have done for absolute value of the inside. That's where x's can't be negative anymore. These go away. And then this side gets reflected across the y-axis for that complicated reason I was explaining before. It basically makes the Minnetonka M, Minnetonka strong. Raise your hand if you had that right. Okay, good. Then we go back to the other way, which is the absolute value of the outside. That means you're going to take all the y's and make them become positive. They were negatives, they're going to become positives. So it looks like this. This part down here has to go up there. This part will stay the same. This part that was down has to go up. And it makes this funky looking sort of M shape. There, that's green. Raise your hand if you had that one right. Sweet. Then you only have one more thing to learn. And that is how to find 1 over the function. For this, I'm going to give you just a really simple one to start with. Let's say it goes like that. And let's say it goes up as high as 2 and down as low as negative 2. So the red function is your function. First thing you need to understand, we're taking our function, which was this red one, that was f of x, and we're doing 1 over that. So what is the f of x, the y, right there? 1. What's 1 over 1? So the new function, which I will make in black, shares that point with the old function. What is the only other place where 1 over the function is the same? Negative 1. Because 1 over negative 1 is also negative 1. Those are 2 important spots. That's the only places our graphs will ever touch. Okay, next, what if the f of x is 2, like here? F of x is 2, so it's not 2 anymore. It's 1 over 2, which is 1/2. Halfway between 0 and 1. Here's a weird spot. The function is 0 right here, so then our inverse is 1 over 0. Well, but that's a naughty. You can't have 1 over 0. So asymptote right there. You are correct. Nice gut feeling on that one. There's an asymptote in our graph right there. Because at that moment, f of x was 0, and 1 over 0 can't exist. And the last is, as this gets really small, do you get f of x is like 0.1 or something really small? Do you get that 1 over something really small becomes actually big? 1 over something really small. 1 over 1/10 is 10. 1 over 1/100th is 100. So as this gets really, really small, this gets really, really big. That black graph is the inverse of the red graph. Let's see if you can handle the other part. Where would this, there's one of the dots. Give me some more. Give me another important spot where f of x is -2. Where f of x is -2, you'd get what? -1. No, wait. -1/2. Thank you. And then where this gets really small, this one gets really big. That's the inverse of the red graph. Okay, I'm going to show you another one. That's called the sine graph. If I do inverse of it, it's 1 over all these spots. The highest it goes is 1. Lowest it goes is -1. Where you should start is where the inverse can't exist, which is when f of x is what? When f of x is 0. Here, here, and here, the graph can't exist. You get 3 what's then? Asymptotes. Asymptote, asymptote, asymptote. So it's all about making those asymptotes and then finding the spots where the two graphs are going to cross. When is f of x the exact same thing as 1 over f of x? 1. And what else? -1. Those are the only spots where those graphs will ever touch. And the last thing is to get the concept that when f of x gets really small, my y's are getting really small, the other one gets really big. So I'll do this in green. As this gets really small, this gets really big. Goes through that spot's the only spot they touch. And can you see what's going to happen here? Down here, as this gets really small, this gets really big. There, you just did the inverse of sine. We'll do that again someday, and we'll call it cosecant. But you don't really have any clue what that means right now, so it's okay. But do you get, we just graphed the inverse of the red graph. We did its inverse. We did 1 over it. All right, let me show you your homework. It's a lot like that. And granted, that last one, I know from the silence in the room, that's stretching you a little bit. And that's the only thing that I think is challenging it at all on the next test. Okay, so just understand that it's not like the whole test is like that. There might be one question like that. There's a lot of other questions on other stuff that you're already good at, like transforming a point from one spot to another, or absolute valuing on the outside or the inside. That other stuff is not nearly as hard, so don't stress about the one hard thing. All right, so get to the first part of the assignment is right here. Do you get this is just a parabola because it's got a squared that's been moved to the right to, what does this make happen? It's flipped upside down and it's moved, notice this is a +4. What's that mean? So here's my parabola, and it's moved where? What's that mean? Right to. What's the negative do? Flips it. What's the positive 4 here do? What's it up for? There. I've graphed my first one. I want to be a little more careful. I can put in actual points. Over 2 and down 4. And if you want, all you have to do is make an XY chart. The other day I told you XY chart is your best friend in graphing. So if you got a little lost on that, just stick in like 2 and see what happens. You get 0, and you got 4 minus 0 is 4. Okay, so when I stick in 2, I get 4. Over 2, up 4. That's that spot right there. Just find some points. It's really not that hard to just stick in some numbers on your XY chart. 2 gave me 4. Let me stick in 3. 3 minus 2 is 1. 1 squared is 1. 4 minus 1 is 3. 3 comma 3. Over 3, up 3. That's that spot right there. And keep on going and make more dots. Okay, so if you get lost in your graphs, just make an XY chart. Easy peasy. Okay, then the next part was take the absolute value of it. Did they absolute value the y's or the x's on this graph? The y's. So this graph, if I continue, it goes like this. Do you get where the y's were negative and are now going to have to be positive? So your new graph for this one is going to roughly look like that. That's for 3B. All right, I don't want to do your whole homework assignment for you, but you're going to do that page. You're going to skip the pink page because there's got too many of these. We don't need this many practice problems of those. So skip the pink page. Go on to this page. Notice it just says describe the transformations. Doesn't say to graph it. Describe it. In this, it got moved where? Right 3 and down 1. Done. What's different about this one? Absolute value, which means all the y's, just if you're describing it in words, all the y's become positive. And then how would you describe it when you do the absolute value of just the x's? And you can do it from there. I'm not doing your whole homework assignment for you. This is kind of like the inside function, the inside of a function versus the outside of a function. They've got the person's face inversed. All right, anyway, somebody, grad student with too much time on their hands. So here's one where they want you to make the inverse of it. Do you remember me saying that you go where it's 0 is really important because then 1 over 0 can't exist, so there's asymptotes there. You might want to start by putting in asymptotes right there, and there, and there. And the other points I said was important, the only time it'll ever be the same as itself is if f of x is equal to what? 1. When there's a 1 right there, then 1 over 1 will be 1. So 1 and negative 1 are the only important points. Those are the spots right here where your graph will overlap with the other. And then generally speaking, it's something like that, but I'll let you figure out how to finish it. All right, you're doing that one and this page, and that's it. After that, you may cross off all the rest. That makes your assignment reasonably sized. And get it done, please. You have a long weekend. If you don't do some stuff over the long weekend, you'll come back Monday and be lost. That would not be good. I need you to come back Monday, practiced up, so that I can do one last set of practice problems with you on Monday, and then we take test Tuesday. It will be one of the easier tests you've taken, as long as you understand what I just taught you today. And that inverse thing is only one thing you have to know out of many. Okay, that's all I got for you for today.